So let's take a look at polar coordinates. And the general way I like to think of polar coordinates is that it's an alternate coordinate system for describing the flat two-dimensional plane, or R2. Um, so let's talk about why we might want to do that and how we use it. So um, most cases, a natural way to do it, to describe the plane, is just using XY coordinates, describe a graph using XY coordinates. It's not always true. So for example, a natural way to describe a circle is, assuming center at the origin, is just to give the radius, say r equals 4. So just write r equals 4 and notice that it completely describes a particular graph, a circle. Also, suppose you have a straight line through the origin. There's a simple way to describe that by simply saying what is the angle that it makes with the x-axis. So if you have theta equals pi over 4, that immediately tells you what your entire graph is. So sometimes using r and theta to describe a graph using this sort of setup is beneficial, and let's talk about how to do that and how to use it. So, formal statement: any point on the plane can be defined by r comma theta, where r is the distance from the origin, and theta is the angle formed with the positive x-axis by the line through the origin and the point. Using the system, this is called polar coordinates. Okay, so for example, so let's plot these points. And these points are given in polar coordinates. So personally, I find the easiest way is first to go through what the angle, think about the angle, and then think about r. But you can do it either way. Okay, so the first one says the angle is pi over 2. So I'm going to be going straight up the y-axis, and then I have to go 3 in that direction. So imagining that I'm going 3. Here's my point A. Okay, point B says my angle 5 pi over 4. So notice that's past, let's see, so that's more than halfway around. So in fact, that's down here, and then I have to go out 1. So that'll take me out to about right over there. And there's the point B. Okay. And finally, the tricky point C. Point C says face in the pi direction, which would be, for example, along the negative x-axis, but go -2 in that direction. So what does that mean? Kind of means we have to go backwards. So that would put us over here. Okay. So that's roughly speaking how polar coordinates describe the plane. Okay. And also note that if r equals 0, the point is at the origin, and the angle doesn't matter. And we sometimes don't even give it. Okay, so that's the basics of what are polar coordinates. Next, we already have rectangular coordinates, x, y, and now we have polar coordinates. It's important to understand how to go back and forth between the two. And we can do that in straightforward fashion if we just think about the definition of trig functions. So we're going to use the fact that sine theta equals y over r and cosine theta equals x over r. And solving out from there pretty much gets us the whole way. So notice that we can, from that, directly solve for x and y respectively. So we know that y equals r sine theta, x equals r cos theta. So that tells us how, if we're in polar coordinates, how do we say what the xy rectangular coordinates are? Now let's go the other way. So this is a little trickier, but we have to use another identity. So note that we know that x squared plus, we use the picture here, note that x squared plus y squared has to be r squared. And so from that, we can solve for r directly. It's the square root of x squared plus y squared. And then to solve for theta, we want an equation that involves only theta, x, and y. There are various ones that we can use for this. The typical trig function to use is tan. It's pretty convenient. It's just tan of theta equals y over x. Therefore, theta equals arctan y over x. So one small comment is that you should recognize that tan is a periodic function, and arctan only gives you values for theta from negative pi over 2 to pi over 2. That's obviously not necessarily the case for every theta you might deal with. So the technical definition is that theta equals arctan y over x plus k pi for some integer k. But in a given scenario, if it's important, just double check what your angle theta is supposed to be. Okay. So put it all together, here's the formula. If you're starting in xy coordinates, then r comma theta equals square root x squared plus y squared comma arctan y over x. And if you're starting in polar coordinates, then your rectangular coordinates, xy equals r cos theta, r sine theta. Okay. And to do that as a straightforward calculation, we'll leave concern about the angle business for another day. So graphing in polar coordinates. So what we can do is we can make an equation, and the usual way is to express r as a function of theta. Not always, but that's the typical way. So here is an equation, r equals 2 cos theta. So first of all, we're going to sketch the graph, and then second of all, we're going to convert this to an equation in x and y. Okay. So once again, if we want to make a graph, but we don't know what the graph looks like, what do? We collect some points. So as I mentioned, in this case, r is essentially written as a function of theta. So let's make a little table. Theta values and r values. So let's pick some easy theta values. When theta is 0, r is just 2. And when theta is pi over 4, r, so it's going to be 2 times rad 2 over 2. So that's just going to be rad 2. When theta is pi over 2, plug that in, you get 0. And then when theta is, let's see, just to get a further idea, when theta is pi, it's going to be -1, so it's going to be -2. This is one of those cases where we're at an angle, but we're walking backwards. So let's try to draw this out and see what might be happening. Okay. So at 0, r is 2, so that gives us this point. At pi over 4, we're getting rad 2, so that's somewhere, let's say around here. Maybe a little further, actually. Let's see. Maybe something more like that. Okay. And then at pi over 2, we get 0, so something like this. And then notice that at pi, we get -2, and that just goes back, that gives us our original point. Okay. Oh, and actually, I want to put one more point on our table just to help us out. What about at 3 pi over 4? So at 3 pi over 4, you punch that in, you're going to get 2 times negative rad 2 over 2. That gives us negative rad 2. So the 3 pi over 4 angle, which is in the second quadrant, we're walking out negative. So it's actually going to give us this point right here. So with those points going in and knowing the way that trig functions behave, I hope it's plausible to say that what we actually get is a circle. If you didn't believe that, you could fill in some more points. But another way to do it, to prove it, of course, is to write this, or prove it for yourself, is to solve this out in x and y, and then see what equation you get. So how does that work? Well, we've got the equation r equals 2 cosine theta. So let's write it out. So we know that r, let's convert to x and y. We know that r is the square root of x squared plus y squared. Now, what is cosine theta in terms of x and y? Rather than working with the trig functions, just looking at the graph, you can see that cosine theta is going to be x over, well, it should be x over r, but we know r is just the square root of x squared plus y squared. So again, you might normally write x over r, but we've got to write everything in terms of x and y, because that's the equation we're trying to write down. So now we can just solve this out. So cross multiply and you get x squared plus y squared equals 2x. And now we've got to do a bit of algebra. So this gives us x squared minus 2x plus y squared equals 0. And we've got a quadratic and we want to sort of solve out what's going on, or I should say degree 2, but in 2 variables. But it's separated really nicely, and we can just, for x, complete the square. And ta-da, this tells you exactly what it is in a form we're familiar with. It's a circle, and the center equals 1, 0, and the radius equals 1, and that pretty well matches with the picture, that with the graph that we drew. So this is the standard thing. Given an equation in r and theta, just replace them. Now, of course, sometimes it's easier to note not to replace theta directly with, for example, arctan of y over x. But if you've already got cos theta, say, oh, I know what cos theta is. Cos theta is just x over r, which is just x over the square root of x squared plus y squared. And similarly for the other trig functions, it's probably easier just to convert the trig function itself. Okay. So this, of course, is a known sort of formula for polar equations in general. So I'm just going to show you in passing some, there we go, interesting sorts of polar equations. Take a brief moment for this. So notice that our circle is one of the choices in the bottom row. There are all these others. These are not things to memorize, but this is a nice handy chart to have. And then so finally to summarize. Polar coordinates, and then those are your 2 basic conversion formulas, either from polar to rectangular or from rectangular to polar.